Hello everyone, welcome to this presentation. My name is Wonjae Choi. I'm an assistant professor at Ewon University in South Korea. Today I will talk about greenhouse gas reductions and economic benefits of using green hydrogen in steel industry. So mainly in this presentation I will try to introduce various ways of using green hydrogen in steel industry, and I will try to analyze the greenhouse gas reductions and economic benefits of each method of using green hydrogen. Okay, so let's get started. First, I want to talk about the background. Steel industry is emitting a large amount of greenhouse gas emissions. It is emitting about 5% of global total greenhouse gas emissions, and it is emitting about 1.85 kilogram of CO2 on average from the production of 1 kilogram of steel. And these large emissions are mainly caused by the fact that they're using coals not only as a main fuel but also as a reducing agent. Because of that, this steel industry has been viewed as one of the most difficult sectors to reduce greenhouse gas emissions. To reduce this large emission, we need some chemicals that can be used in the steel industry and not emitting greenhouse gas emissions. And because of that, we can use hydrogen in steel industry. But there are two main concerns. First, the cost. Obviously, hydrogen is less cost effective than coal. And second, the greenhouse gas emissions from the production of hydrogen. So now hydrogen has mainly been produced by fossil fuels, reforming of fossil fuels such as natural gas, or from the electrolysis using grid electricity, and this grid electricity is produced from the fossil fuels. So in life cycle point of view, this hydrogen production actually emits some quite a large amount of greenhouse gas emissions. So we need to produce hydrogen that is not emitting large greenhouse gas emission from their production. So the electrolysis with surplus renewable electricity has been viewed as the method that can resolve these two main concerns. Because it is using renewable electricity, it is not emitting greenhouse gas emissions from the production of hydrogen. And because it is using surplus renewable electricity, which is inevitably produced in the future because of the intermittency of the renewable power and the large increase of solar PV power generation, the hydrogen production can become cost effective as well if we use this surplus renewable electricity. Because surplus electricity produced from these renewable sources can be very cheap. As you can see in the figure there, in California, the cost of electricity became even negative here because of relatively large production compared to the given demand. So in this presentation, we are exploring the method of using green hydrogen in steel mills, and the green hydrogen is assumed as produced from the surplus renewable electricity with electrolysis, like this. Okay, so from now on, let's look various methods utilizing green hydrogen in steel mills. Before talking about the method, I want to briefly introduce how steel mills are producing steel. So this schematic shows the conventional steel making processes using blast furnacing. In these conventional steel mills, iron ore and cokes, which are produced from the coking process, are input into the blast furnace. And iron ore is reduced by the carbon monoxide. Which is produced from the reaction of cokes and hot air from the hot blast stove. And from this blast furnace,ing it is converted into molten iron. And this molten iron, which is carbon rich and contains many impurities, is transferred to the basic oxygen steelmaking process, also known as Lynch-Donowich steelmaking process. To be purified and converted into low carbon steel by supplying pure oxygen into the process. To produce this pure oxygen, air separating unit (ASU) are often used. Because coking, blast furnace,ing, and basic oxygen steelmaking use chemical reaction in their processes, byproduct gases are generated from the reactions. So coke gas, blast furnace gas, and Lynch-Donowich gas originate from this coking, blast furnace,ing, and basic oxygen steelmaking processes, respectively. Other types of byproduct gases are also generated in the steel mills if the steel mills use a different type of steelmaking process. And these byproduct gases are low quality fuels because they contain a large amount of diluent mostly. So their economic values are not that high. So these gases in conventional steel mills are often gathered and combusted to generate heat, which can be also, further converted into electricity if they have the power plant. Okay, now let's see how to use green hydrogen in steel mills. First, hydrogen can be used in hydrogen steelmaking process. The direct reduction steelmaking process is applied in hydrogen steelmaking process here. So here we're using direct reduction reactor, which just reduce this iron ore into sponge iron. And they are moved into the electric arc furnace because unlike the conventional blast furnace,ing, direct reduction does not melt the iron but directly reduces the iron ore, and therefore it is necessary to melt the iron and add some selected component to make them into the steel alloys. The change from blast furnace,ing to the direct hydrogen reduction requires additional capital investment, such as this direct reduction reactor or the electric arc furnace. And this hydrogen can also be used to upgrade the byproduct gases into valuable chemicals. In this presentation, the processes of upgrading into methane and methanol are analyzed because these are the simplest chemical that can be synthesized. And similarly, in this method, we need also additional reactor, which means additional capital investment to do that. And the simplest method of using this hydrogen is just selling this hydrogen to a hydrogen station that can be, used in the hydrogen vehicle. The advantage of this electrolysis of water is that they are producing not only the hydrogen but also the pure oxygen from here. And this pure oxygen can be used in this basic oxygen steelmaking process. As I mentioned, they are producing pure oxygen from using the air separating unit. So by providing this pure oxygen from the electrolysis, we can actually decrease the use of ASU, air separating unit, which means we can decrease the energy use as well as the greenhouse gas emission associated with using this ASU. Okay, so in this presentation, we are analyzing and comparing four methods that I mentioned in the former slide. And here, hydrogen steelmaking was numbered as method 4, methanation, methanol synthesis were numbered as method 2 and 3 respectively, and settling to the hydrogen station and using this pure oxygen in basic oxygen steelmaking process was numbered as method 1. And here for a simple analysis, we are assuming that hydrogen steelmaking actually using this kind of reaction, and in the conventional blast furnace steelmaking process, they are using this kind of chemical reaction. So the only difference is the carbon monoxide and the hydrogen. And we also assume that methanation and methanol synthesis can be simply modeled as this chemical reaction. Here we assume that all the carbon monoxide and the carbon dioxide can be converted into methane or the methanol based on this kind of chemical reactions. Based on that assumption, we analyze the economic benefits and GHG reduction of applying this 4 method. Okay, so from now on, let's see some of the literature. First, let's see the greenhouse gas emission analysis literature. So here we are assuming the capacity of electrolyzer as 1 megawatt, and we assume that electrolyzer operate 10 hours per day with the surplus renewable electricity. And here we are showing some of the parameters related with efficiency of each process. And here we also have the GHG intensity of electricity, which was determined as the GHG intensity of world average electricity. This shows the basic literature of the greenhouse gas emission analysis. Here in method 1, we have only blue part, which is showing the greenhouse gas emission reduction by replacing the ASU electricity. Because we are producing pure oxygen from the electrolysis, we can actually use the use of the ASU and ASU electricity. So because we can decrease the amount of electricity used, we can actually decrease the greenhouse gas emissions. That is the blue part. And if we see this method 2, methanation, and method 3, methanol synthesis, we have 2 more parts, this orange and gray part. Orange part is showing the greenhouse gas emission reduction by converting the byproduct gases into chemicals. So byproduct gases contains a large amount of carbon dioxide and carbon monoxide, which also will be converted into carbon dioxide by generating heat in conventional steel mills. Because we are using that carbon monoxide and carbon dioxide and convert it into the methanol and methane, we can actually decrease the amount of greenhouse gas emissions. That is the this orange part. And in the conventional steel mills, these byproduct gases were used to generate heat. And because we are using that byproduct gases to make some valuable chemicals, we have to additionally supply some of the natural gas to supply the additional heat to compensate that that decrease in the heat supply, because we decrease the amount of byproduct gases used to generate heat. And that from that natural gas combustion, we have some greenhouse gas emissions, and these gray parts are showing that emissions. In total, this shaded area are showing the total emissions of each method here. As you can see, comparing this method 2 and 3, method 3 has more greenhouse gas emission reductions. And in method 4, this yellow part here is showing the greenhouse gas emission reduction by replacing the coking coal. So here, method 4, we are using hydrogen instead of coal, which we can decrease the use of the coking coal, and we can decrease the greenhouse gas emission that is originated from the coking coal. That is this yellow part. And because in this hydrogen steelmaking process, we are using the electric arc furnace in the downstream of the direct reduction reactor. So in the electric arc furnace, we are using the electricity to melt the iron, sponge iron. So because of that use of the electricity, we are generating some of the greenhouse gas emissions. That is this green part. So in total, this method for hydrogen steelmaking can actually decrease the largest amount of greenhouse gas emissions among 4 methods. This figure shows the greenhouse gas emission reduction according to the greenhouse gas intensity of electricity. And this purple are showing the case of method 4, this yellow method 3, this red method 2, and this blue method 1. Basically, if the GHG intensity of electricity increases, the GHG reduction of method 1 to 3 increases. Because in method 1, 2, and 3, they are actually decreasing the use of the electricity in ASU. So if the GHG intensity of electricity increases, this GHG reduction increases. However, in the case of method 4, because we are using a large amount of electricity in EAF, so if the electricity GHG intensity increases, the GHG reduction of the method 4 decreases. So this line is showing the case of the world average. So in the case of the world average, method 4 has a relatively large GHG reduction compared to method 2 and 3. But if we go into this part, China or the India case, which use quite a large amount of coal in power generation, and which has the larger GHG intensity of the electricity, this gap between the method 4 and method 2 and 3 decreases. Next, let's see the result of economic analysis. Here, this table is showing the capital cost of each component that was used in each method, and we are also showing the lifetime of each component. Based on these parameters, we calculated the capex of each method. So this is showing the capex per year, and if you see this method 1, we have the smallest value in capex because we only have to invest the electrolyzer here, which is shown in this blue part. In the case of method 2 and 3, we have the methane or methanol synthesis system, additional reactor, that was shown in this orange part here. And in the case of method 4, we need hydrogen direct reduction reactor as well as the EAF, electric arc furnace. So in the case of this method 4, we have the largest capex. To consider the operating cost as well, we also consider the prices of these commodities such as the electricity, natural gas, methanol, coking coal, hydrogen, and CO2 allowances as well. So this shows the revenue of each method, as you can see. Here, this brown is showing the amount of capex here. As we have seen before, we have the largest capex in the case of method 4. Here we have this light yellow here, which is the cost by purchasing the electricity. So in this method 4, we have to buy some electricity to operate the EAF. And here in method 2 and 3, we have to buy some additional natural gas to provide additional heat. So this green part are showing the cost of the natural gas. So these are the total cost of this each method. And if we see the light part here, they are showing the profit of each method, because we can, if we see the method 1, we can sell this hydrogen to hydrogen stations. So because of that sale, we can make some large amount of profit here. And if we see this orange part, this is showing the profit that was caused by replacing ASU electricity. Basically, we can decrease the amount of electricity used in ASU, so that makes some profit. And this one are showing these as CO2 allowance sales, because in the case of method 4, we can decrease the largest amount of greenhouse gas emissions. We can sell the largest amount of CO2 allowance here in method 4. And this green part, this is showing the CH4 or methanol sales. And this yellow part is showing that the profit caused by replacing the coking coal. So because we are using hydrogen instead of the coking coal, we can actually decrease in purchase cost, because in the conventional steel making processes, we have to buy some coking coal from outside. That is this yellow part. So in total, revenue are shown in this shaded area here. And as you can see, the revenue of method 4 is the smallest. We have the largest capex in this method 4, so we have the smallest revenue. Compared to method 2 and 3, the GHG reduction of the method 3 was larger than GHG reduction of method 2. And here we can see that revenue of method 3 are much larger than method 2, because methanol is more valuable than this methane. And in this case, the method 1 has the largest revenue, because hydrogen is very expensive in hydrogen station. So this method 1's revenue is the largest. The result of economic analysis mainly depends on the price of the commodities. And we are expecting the changes in the price of this commodity, especially for the case of the hydrogen and the CO2 allowance. So here in the last part, I want to show you the result of future prediction based on the future predictions of these prices of commodities. And this table is showing the predicted price of commodities according to the references from the USEIA mainly. And we also referred some other references in the case of the CO2 allowance as well. And here, as you can see, the price of the hydrogen is decreasing in the future, and the CO2 allowance price is increasing in the future. And here we have two scenario reference and large GHG reduction scenario. So in this large GHG reduction scenario, we assume that countries around the world are pursuing a larger GHG reduction, so that the CO2 allowance price increases more rapidly in the future. Based on these parameters, this shows the revenue of each method in each years in the future. So as you can see, the revenue of method 1 decreases because the sales price of the hydrogen decreases. And this other three methods revenue increases in the future, mainly because of the CO2 allowance price. Increase of the CO2 allowance price. And in the case of method 3 and method 1, there is actually a cross here around the 2030 because this method 3 has a large GHG reduction, so that it has some large profit from the selling the CO2 allowance, and this hydrogen selling method is decreases its revenue according to the decrease of the hydrogen sale price. And here, as you can see, the revenue of method 2 and 4 becomes almost the same in 2040 based on the predictions of the commodities price. Okay, so here comes the conclusion. Among the four methods, method 4 offers the largest GHG reduction. Method 3 has a somewhat larger GHG reduction than method 2, and method 1 produces the smallest GHG reduction. And the GHG reduction of each method were calculated according to the GHG intensity of electricity used in steel mills. The difference between the greenhouse gas reduction of method 4, hydrogen steel making, and those of other method decrease if using electricity with large GHG intensity, such as the electricity of China and India. And among four methods, method 4 requires the largest capex because it requires a new reactor as well as an electric arc furnace to replace the conventional blast furnace. And method 3 has a somewhat larger capex than method 2. But method 1 currently has the largest economic revenue because of the expensive hydrogen sale price, and method 3 has a larger revenue than method 2 because the economic value of methanol is greater than that of methane. Method 4 currently has the smallest economic revenue, although it offers the largest decrease in greenhouse gas emissions. And the revenue of method 3 is expected to become larger than that of method 1 near the year 2030 because the prices of hydrogen and the CO2 allowance are predicted to increase and decrease respectively in the future. And the revenue of method 4 is predicted to increase in the future because of the expected increase in the price of the CO2 allowance. That was all I prepared, and here is the acknowledgement, and thank you for your attention. If you have some question, please send me the email to this email address. Thank you.